Now we can learn a certain amount about magnets and magnetic fields by just recognizing that they behave very much like electric dipoles in their interactions with each other. But there's not a lot new there. What is exciting is to learn how magnets react and affect charges. So suppose I have a small positive charge here, and it's near some kind of a magnet. So a couple of things that we notice. First, this charge will experience a force only when it's moving. That force is always proportional to how much charge is there. Thus, a larger charge will experience a larger force. And it's proportional to how fast the charge is moving. A faster charge will experience a faster force. Another interesting thing is that that force is always perpendicular to the velocity. It never pushes with the velocity, it never pushes against the velocity. It's always perpendicular to it. So if I'm moving this direction, I might get pushed up, down, into the page or out of the page, but I would never be pushed in the direction of motion or against the direction of motion. That doesn't happen. Finally, and perhaps most interestingly, there's always a direction, maybe like that, where if it's moving along this particular direction, along this axis, there is no force. And if it's moving away from that axis, say we move along an axis this way, then the force is proportional, yes, to the charge, yes, to how fast it's going, but also to the sine of this angle right here between the axis where there is no force and the direction it's moving. QV sine theta. Well, that's really interesting. This says that when we're moving 90 degrees to that axis, we'll get a maximum force. So what we like to do is we can say, let's define a magnetic field in terms of that maximum force. So the magnitude of the magnetic field will be the maximum force, so when sine theta is 1, divided by the magnitude of charge and the magnitude of the velocity. That'll be our magnitude of magnetic force. For direction, we will say that the magnetic field points in that direction where we would get no force. In other words, if the velocity were moving in the direction of the magnetic field, we would see no force whatsoever. Suddenly, it's starting to look like the force is equal to the charge times the velocity crossed into the magnetic field. Saying that the magnetic field has to be along the direction along which we get no force gives us a choice of two possibilities. Okay, the velocity, there would be no force if it moved this direction or this direction. So I can choose either of those two directions for my magnetic field. If I choose the right one, I can choose it so that the direction of the force, always being perpendicular to this velocity, and it's always perpendicular to this axis, will fit this formula. We just have to choose it so that the right-hand rule gives us the right direction for the force. So that's what we see here on this slide. The magnitude of magnetic field is just the maximum magnetic force divided by the charge times the velocity. And we choose its direction so that the direction of the force is given by Q times velocity crossed into magnetic field. Reviewing cross products for a moment, remember we start with our fingers pointing along the direction of the first thing in the cross product, V in this case. We hold our hand in such a way that we can freely and easily, bending at the knuckles, turn our fingers into the direction of the second vector, the magnetic field. And then our thumb will point the direction of the result. In the case of our equation, force is Q V cross B. If it's a positive charge, the force will be in the direction of V cross B, just as we see up here. V cross B is up, the force is up. If it's a negative charge, then we have a negative here, which flops the direction and means the force is opposite the direction of V cross B. This is very much how the force from an electric field was equal to the charge times the electric field. If it was a positive charge, it was pushed in the direction of the electric field. A negative charge was pushed opposite the direction of the electric field. Last comment here. We said that the force is always perpendicular to the velocity. That means that it can cause the moving charge to move, to turn, but it cannot make it speed up or slow down. Because remember, way back in Physics 101, that it was the component of force that was parallel to the velocity that made us speed up or slow down. The component that was perpendicular made us turn left or right. So if I have a beam of charged particles accelerated by a voltage, when I put a magnet near them, they will turn, but the magnet will not make them speed up or slow down. This is used a lot in particle detectors. We may have particles, such as electrons and positively charged electrons called positrons, moving in a known magnetic field. By measuring the way they turn, we can figure out their charge, and by measuring how much they turn, we can figure out how fast they're going.